Hey guys, this is Sao here. So this will be the one of the first uh, blog videos, I guess, to show you guys how the development of Lisbeth 3.0 is going. And I'll be talking about different things on each blog video. And I guess if you're interested in this kind of stuff and to see how the development is progressing, then this is a good way of showcasing that. Um, so in this video, I'm thinking about talking about flight. Because as you know, one of the most important parts of Lisbeth is its ability to fly, since a lot of nodes are on flight zones. And well, I started making a flight solution about, I don't know, like 4 months ago. And about 1 month ago, I actually stopped developing it because I had to work on other things. And now that I actually can retake Lisbeth development, uh, I'm hearing rumors that Mashtag is gonna implement flying into the new Reborn body for Stormblood. So maybe this is not what I'm gonna end up using. If the flying solution that Mashtag implements on Reborn body is good, then I'll use that. But if it's not good enough for Lisbeth, then well, I have a plan B basically. So I'll be sure that Lisbeth will fly either way. Um, so yeah, basically what I'll be showing you is how I implemented the flight solution and explain a little bit about the algorithms behind it for those that are interested in that kind of stuff. So as many of you know, Lisbeth 2.0, the current version that you're using right now, can fly on Heavensward zones. But the flight solution that I implemented, that was about 1 year ago now, was actually a very cheap, simple way of doing it. Um, I just wanted to make something quickly for Heavensward, and that's one of the easiest ways you can implement flying, but it's also very inflexible and it has a lot of problems. So how the current flight system in Lisbeth 2.0 works is that back then I actually made a bot base called the Lisbeth measure. And this bot base, well, I would start the bot and fly on top of a hotspot. So let's say I'm interested about killing those mobs, right? For Lisbeth grind, for example. Let's say, for example, those the deep eyes. So I would fly around the deep eyes, all around the hotspot, and the Lisbeth measure would create like a trail of nodes and raycast between the nodes to connect to them. And what this made is like a grid on top of the ground. And so basically, when Lisbeth teleports, say, to here and then has to fly over there would be a trail of nodes going from the teleport either right into the hotspot, and then on the hotspot there would be this grid above it. And of course I had to handle things like taking off and going into the grid and going away from the grid and into the ground and stuff like that. But the major problem with this system is basically two things. The first one is that it's very tedious for me to actually mesh. Well, it's not really a mesh, it's just the grid, right? To grid out hotspots, because I actually have to fly around. I have to make sure that there is enough nodes and so on. So it's actually a very tedious process to do it. Then the second problem and biggest problem with this system is that Lisbeth can only fly when there's a grid of nodes above it. If Lisbeth finds itself, say here for example, where I didn't mesh, then it cannot fly, it cannot take off because there's no grids around that. There's no nodes around that to get into the grid system. So it actually has to teleport to the aetheroid, because in every aetheroid there is a path. And the other problem with that is that the the paths between hotspots then are fixed. So for example, if there's a hotspot here, yeah, let's open the map. There's a hotspot here. There's another hotspot here. there might not be a direct trail of nodes between them. It might be that that Lisbeth has to go to another hotspot here where there is a trail, and then to these other hotspots through this trail. So it's, I could trail this too, but then, it was a mess, really. It's a very inflexible system, and it's not something I wanted to continue with Lisbeth 3.0. So I spent a couple of months developing a flight solution, and basically, the new way of flying is through an obstacle graph mesh. So what happens is, I had a few guidelines for the design of the system. The first one was that I wanted the system to have mesh files that were very small, or no mesh files at all, but still be able to fly all over the zone. So how I accomplished this was using an obstacle detection technique. So basically, how that works is, now let's go to the code. Now let's see old one. Basically, how that works is that I'm using an A-star Pathfinder that I made. This would be better implemented with a D-star Pathfinder, but that's the conversation for another day. And how it works is that let's say there is no mesh file, obstacle mesh file. So Lisbeth finds itself here, right? It has to fly, let's say, here to kill mobs, right? The deep eyes. So what happens is, Lisbeth is going to A-star Pathfind to the deep eyes. And it'll take off, and it'll start flying from what it thinks is the optimal path, right? And then it'll detect that there's an obstacle in front of it, that the path is actually blocked. So what it does is it stops, it raycasts around it with a kind of a flood fill algorithm, and it records all the obstacles around it, and then it saves those obstacles in a file, in a mesh file on disk, and then it recalculates the optimal path. It pathfinds A-star again, this time taking into consideration the obstacles that it just saw. So this time it'll try to go like this, for example, and then it'll find another obstacle. It'll stop again, raycast, save all the obstacles, and start flying again. And so what this causes is that, one, Lisbeth should get to its target, even if there is no mesh file. But it'll look clumsy, right? Because it'll be trying to go through obstacles that it doesn't know yet about. And it'll stop, it'll raycast, it'll try to go around them, then find another one, stop, raycast, and so on. But it will get there. That's the important part. It's the important guarantee, I guess, of this system. Because even if it's clumsy the first time it can get there. And then the second time, because the mesh is saved on a disk, on a file on the disk, and it loads that mesh on whenever it enters the zone. Then the second time it tries to fly to the hotspot, it'll know already about all of these obstacles. So the first pathfind will pathfind a path that goes around them, and it won't look clumsy anymore. It'll just, fly normally. And of course, maybe the next time it tries to go to that hotspot, maybe, because it now knows there are obstacles here, but it doesn't not know yet that there are obstacles here. What happens a lot is that the Pathfinder will think it's faster to go through here, through this side, because there are no obstacles, and so it's found a better path through here. And so the second time, it might still look clumsy, because it'll try to go where it didn't go before. But then the third time, it'll see that there are obstacles in both sides. So the Pathfinder will find a path around them, instead of trying to, find a path around a part where it hasn't meshed yet. That might happen in the third time or in the fourth time, depending on the Pathfinder, how the Pathfinder sees the area, right? So this is very important because it allows for smooth flying by meshing the zone as it goes, but it meshes only the parts of the zone that it's interested in. So what this results is, for example, this is the perfect zone to show that. Is that, for example, there are parts of the zone where really there is no point in meshing. For example, this part. There's nothing here. So why mesh it? It's just a waste of bytes, and it's just making the mesh file bigger than it should be. And again, it meshes by usage. So basically, if Lisbeth is not interested in a part of the zone because there's no gathering nodes or no grind mobs or whatever here, it won't mesh that. But let's say there's another bot base, let's say a questing bot base, and there's a quest here. The questing bot base is going to be using this part of the zone, and it'll mesh that. And so each application meshes the parts of the zone that they are interested in, resulting in smaller mesh files. And this was important to me because I didn't want to distribute, 10 megabyte files for each zone. But again, the biggest, most important part of this is the guarantee that even on the first flight, even though it'll look clumsy, it will get there. It's not going to get stuck. Well, sometimes it does happen that it gets stuck, but that's because of the raycaster, and some textures in some parts are difficult to raycast through. And I implemented safeguards in that. For example, if it really feels like it is surrounded by obstacles, it can happen when, well, I guess there's no easy way to demonstrate that here. For example, it might be stuck somewhere like this, and there's also a ceiling, imagine that, and there's only a small way to get out. It'll feel like it's completely trapped and won't find a path, then it's just going to teleport. It's like a safety measure, I guess. So there are safety measures, and sometimes it might get stuck, but the thing is, it'll teleport out because it couldn't find a way out after meshing that part. But then when it tries to go to where it was trying to go in the first place, it'll already see those obstacles where it got trapped. So it just won't go there, and it'll take another path. So essentially what this guarantees is that it will get there, and that's very important because on the previous flight system, it couldn't. If there was no grid on top of it, then it just couldn't get into the grid and fly. But now, it will fly. Yeah, it will simply get there. And it'll look clumsy the first few times, but then as it does it more and more, and learns the lay of the land, so to speak, then it'll get better and better, and eventually it'll get as smooth as you can do it with a mesh. The second part of this is that I decided to mesh the obstacles and not the empty space. That's because obviously there's more empty space in a zone than there are obstacles. For example, even though there's all this ground area here, you really don't care about meshing nodes that are below the ground, because you only really care about the surface of obstacles. So it ends up with smaller meshes than having to mesh, than having to pathfind through the empty space. The way I do the pathfinding, so let's go to the code then. This is the new Lisbeth, which just has a UI. Let me find the Lisbeth. Yeah, I have like 4 different Lisbeth folders. No, it's in the new folder. Here we go. So how I ended up implementing this is, first I use an octree to partition the entire zone. So basically the entire zone is represented as a single big cube. The cube is like, I think, 1024 yalms in length. That covers the entire zone, because what I noticed is that in Heavensward at least, I don't know about Stormblood, I'll have to adjust to that. In Heavensward at least, zones never get further than 1024 yalms in any direction. So basically how the octree works is that the entire zone is considered into a cube, and then subdivided or partitioned into octates, into 8 cubes, smaller cubes. And then those smaller cubes are partitioned into their octates, into 8 smaller, yet smaller cubes, and so on until you reach whatever you want your unit cube to be. In my case, I found that the good size for the unit cube was 5 yalms. I don't know if 5F is exactly 5 yalms in the game. I haven't figured that one out, to be honest. Yeah, 5F. Let's just say 5F. So basically, the most important part about the octet system is that lets you find where you are and where your target is in the zone in a very fast manner. Because if you were to partition the zone into 5F cubes, you'll get like 1 billion cubes for the entire zone. And if you were not to use an octet, if you wanted to find in what cube you are based on your XYZ position, you would have to compare every cube until you find the one you are in. You would have to basically make a, is position inside cube comparison for hundreds of thousands of cubes until you find the one where you are actually in. But with an octree, you don't have to do that, because how it works is that, well, you have to do comparisons, but you only have to do a set amount of comparisons. So for example, what you do is you first grab the biggest cube that represents the entire zone, right? And you'll always be inside that. If you're outside the zone, then there's a different problem. You'll always be inside the first cube. So then you partition the big cube and find in which of the 8 octets you are in. So that's one comparison. So you take this octet, for example, in our case right now, and then again you partition this into its octets and find which one it is. That's another comparison. But the point is, instead of having to do hundreds of thousands of comparisons with the small cubes, we are doing just a set amount, right? For example, 8 comparisons to get there. So that makes it viable, basically. Otherwise, it would be way too slow. There's another important part about the octet that I found out later, and it's that it allows the Pathfinder, the A-star Pathfinder, to abstract empty space into bigger nodes, because every node, every 5F node in the zone has a parent node, right? The previous octet on top of it, so to speak. The root node is the entire zone. Then, for example, the octets of the entire zone, which are big parts of the zone, those are the children of the root node, and so on. So it's the octree, it's the form of the octree. So what this allows is that if a big node, not the unit nodes of 5F, but one of the bigger ones, has all of its children empty, then the Pathfinder can consider that big node as a single node when pathfinding. Because it has the guarantee, and this is important, it has the guarantee that if you are in any point inside that big node, and want to go to any other point inside that big node, since the node is completely empty, it will always be able to do that on a straight line. So there's no need to pathfind within an empty node. It sounds very obvious, right? But when you're actually implementing the Pathfinder, it's something I didn't know before, and by researching stuff about how pathfinding is done in games and all of that, I realized you could do that. Different people do it differently, but it's a very common technique for pathfinders in games to do this kind of big grain and then fine grain pathfinding, because zones can be too big to do just a fine grain pathfinding. So if the zone was considered only as those 5F cubes, then there's like 1 billion nodes in the zone, and the pathfinder has to pathfind through them. But there's the octree is just a method, to abstract some parts of the zone into a single node, reducing the amount of searching that the pathfinder has to do. Let me start showing some code here. Resources, flight, octree. So again, I had to struggle about how I wanted to represent the octree. I considered many ways. I revisioned it. I refactored it. But yeah. Oh, and this is one of the nice parts about an octree too, is that the nodes are not explicit. Rather, they are implicit, because the structure of the zone is implicitly known by the partitioning of the octree. Because you can do the partitioning for the parts you're interested in real time. You don't have to. How do I explain this? On a normal pathfind, the nodes are explicit. Like you have one node in XYZ here, you have one node in XYZ here, You load those explicit positions, and then the Pathfinder finds paths through those nodes. But here, the nodes are implicit, so the Pathfinder finds which nodes it can go to in real time by just simply doing a very simple calculation, which is in an octree, since the nodes are regular on set lengths, then if I go 5f on a straight line in front of me, I'm on this node, like on the adjacent node of the one I'm currently in. If I go 5f up, I'm on the up adjacent node. If I go 5f down, I'm on the down adjacent node. So the position of the nodes don't need to be explicitly stated anywhere. The Pathfinder knows implicitly which node is adjacent to which other node, just based on their positions. So this is very important because, again, it means it makes the mesh smaller. So yeah, there's a lot here. Honestly, it's not that important. I guess there's methods like this if a point is within the bounds of a node. That's another thing that helps, is that on an octree, the nodes are bounding boxes and they are regular, so that's why you can do stuff like this. Um, you know, surroundings, you get the octree, you get the levels. This is I use this for the raycasting. To get, this is like, this method here asks the octree, hey, find the nodes that are around me up to this amount of levels. Stuff like that I had to implement. Get right links, and all of this is used for finding the plane of nodes. I guess that I'll show that once I show this. It's easier to visualize. Yeah, basically that's the octree. I had to also make an occ node to calculate the octates of an occ node and form the tree structure that way. What else? So here's the Pathfinder then. It's a very simple A-star Pathfinder. Let's delete that. It uses a slightly how is this called? I don't remember, but it's basically when the heuristic is not exact, so that you're not really finding the optimal path, but you're finding a good enough path. That's just good enough for games. That's another technique that a lot of games use, because you really don't care to find the absolute optimal path from one point to another. You only care to find a good path, and doing it this way with this heuristic, it makes the entire search faster. You get your G's, you get your H's of the heuristic, and you get your path, right, the loop. I had to implement some stuff to make this fast enough. For example, where to store the nodes is actually very important, because if you store it, for example, on a list, it's incredibly inefficient to get the nodes based on their score and stuff like that. So I had to do a heap. Let me see. Where did I put that? Structures, I think. Yeah. Fast priority queue and all that. Well, I didn't write this heap stuff and queue stuff. These are just data structures, and there's a lot of examples of that elsewhere. It's a binary heap, I think, basically what I ended up using here. Fast priority queue node, all of that. So it's a fast priority queue. It's to make the pathfinding faster than what you could do with a simple list or a simple queue or stuff like that. Yeah. So basically, here's the while loop. Yep. So basically, it's just an A-star Pathfinder, and I guess the only difference between this A-star Pathfinder and a different A-star Pathfinder, and the reason, for example, why I can't use the Reborn Body A-star Pathfinder, is because, again, the nodes are not explicit. I don't pass to this Pathfinder an explicit set of nodes with explicit connections. Rather, the Pathfinder understands that it's an octree it's navigating, and so it implicitly, generates the adjacent nodes based on the position of the current node. I guess we can see that on the expand. Let me find the expand here. Oh, it's in the octree, right? Here. For example, traditionally an A-star Pathfinder, when it expands a node, to start evaluating the adjacent nodes to see where it can go, traditionally it uses some kind of explicit map, right? This node is connected to these other adjacent nodes. You can go to these other adjacent nodes, and that's how it finds the adjacent nodes and evaluates them. But in this case, it's asking the octree which nodes are adjacent to this one, and the octree here, and the octree is finding those adjacent nodes based on the regularity of the bounding boxes of the octree. And here's the cool part about what I was telling about how you can abstract empty smaller nodes into their parent node, where I named it supernodes. Basically, you can name them whatever you want. And basically, a supernode is the topmost node in the octree for whom all unit nodes all the way down are empty. So basically, the Pathfinder searches through supernodes, not really the unit nodes. And if what this causes is when there is a big ass empty space like this one, Pathfinder only saw one node. It didn't see all the 5F unit nodes here. It just saw one node. And that it was empty, so it could travel there. Then when it approaches an obstacle, what the Pathfinder sees is actually the unit nodes. It's fine-grained around obstacles, but it's big-grained when there's no obstacles. That makes the search much faster than it normally would if you only consider the unit nodes themselves, the 5F nodes. So yeah, basically, that's it. That's basically what this does. And then the Pathfinder spews out, a path, a set of nodes that you can follow to get from point A to point B. There is a little bit of post-processing stuff here. It smoothes the path because the Pathfinder moves in 6 directions, right? It moves up, down, left, right, front, back. It doesn't move in diagonals. So the path that the Pathfinder spews out is actually very cubic, let's say. And then what I did was implement a very common way to smooth out a path. You simply raycast, which I had to implement too. That's good. Just a simple raycast function that uses the mesh that Lisbeth generates, and raycasts through that mesh between 2 points to see if it hits an obstacle. Basically, what the Pathfinder does then to smooth out the path is a very common technique that if you can raycast from point A to point C, you can skip point B. So it removes point B from the path. And then again, if you can skip from point A to point D, you can remove point C in between, and so on. So basically what you end up with is a path that has only the relevant nodes. Relevant nodes are nodes where there is actually a transition, and usually in corners. For example, if I wanted to go from here to say here, the Pathfinder is going to move something like this, right? In a very cubic way. First front, and then straight up down. I can't do that manually, but yeah, straight up down. With that kind of, and it's going to have nodes, a lot of nodes on the path. That kind of smoothing technique, what happens is Pathfinder is actually going to find a node here that it can raycast to. It's going to skip all the nodes straight on top and find the node that it first can raycast to. So it's going to go on a straight line through the corner, then on a straight line to the target. Instead of, going in a very cubic way through a lot of nodes. So that's important. What else? So yeah, it's basically an octree, an A-star, and the third part, the important third part, is the raycasting. And let's see where that is. Routing, no, that's the area router. It's been a month since I had to look through here. Mm. No, it's on flight. I think it's on flight. No, not that. Oh god, where was that shit? Oh yeah, it's on flight. Obstacle graph. That's the actual obstacle graph. This is what I save. I do it on Protovov to make it smaller. The obstacle graph, as you can see, it just specifies the octree. It specifies the max bound, the min bound, since the octree is again a bounding box. The center, that's important. The length, the unit length. Oh, I was actually ended up using 4F instead of 5F. Yeah, I thought it was 5F, but it's 4F. It's been a while. But yeah, I have to save the obstacles though. And that's what takes the most memory. I'm saving a vector of obstacles, but the nice part about the octree is that I don't have to save the cubes. I have to save just the center of the cubes. And the octree can find where the centers are. Yeah, that's basically the obstacle mesh. And the debug data, which I use for something else. I'll show you later. Where was the actual flight? Was it in navigation? I don't remember. Travel to. No, those are the abstractions. No. Where was that? Yeah, it's been I should have been working on Lisbeth earlier than this, but I guess what it is, it is what it is. Well, it doesn't matter. Somewhere in there, flying. There we go. There we go. Was the raycast here? I thought it was elsewhere. No, it's here. It's here. Recalculate. There we go. So basically, what happens is the flight methods. Let's see. What's the entry point? Yeah, it's this one. The flight methods. You can see it actually uses the player mover to go from one point to another, which is the ribbon body method of moving from one point to another. This is the while loop that flies. It has many ways to exit the while loop. It considers. I have to consider a lot of stuff, like if there are hostiles around, if I'm in combat, if I'm dead. So it escapes the while loop with different circumstances. The condition, or when you stop the bot, a global stop flag stops every routine that Lisbeth uses, and so on. Yeah, there's been a lot of stuff in here, but basically, let's see, hostiles, path, right. So if the path is null, that happens when either you start or it detects an obstacle. It has to recalculate the path, and let's see where exactly the raycast happened. There's escape mechanisms and all of that. No. Get corrected start. Oh yeah, that was a big problem. Detect obstacles. Here it is. So basically, it makes a raycast to all adjacent nodes and detects obstacles inside those nodes, and then that's basically how the area gets meshed. Now, I guess we can see it in action. Finally. Let's see here. Whoops. I have to log into Ribbon Body, so that means I have to cut the video here because I don't want you to see my key. I'll see you in a bit.